Welcome to Friday Night AI. My name is Rada Mihalcea. I'm a professor of computer science at U of M and also director of the Artificial Intelligence Lab. And on behalf of the AI Lab, we are thrilled to have you here. We started Friday Night AI earlier this year with the goal of facilitating a conversation between the local community and what researchers in AI are up to. And for tonight, I'm very happy to have a conversation on how to go about teaching robots through natural interactions. Before I delve into that, I'll tell you a little bit about the format. So the way we'll go about this conversation, we'll start with some introductions, and I will ask a few questions, and then we'll open it up to you. So if you have questions, please remember them for later. So with that, I'm really happy to have here the experts in teaching robots through natural interactions. Professor Joyce Chai. She is a researcher in natural language processing and also intersection with robotics. And she directs the Language and Interaction Research Group. And she's focusing on grounded language processing. Also, Professor John Laird, who's the John Tishman Professor of Engineering in Computer Science and Engineering, and he directs the SOAR lab. He also co-founded SOAR Technology, an Ann Arbor company, and we have here representatives from the company, in addition to John himself. And I would like to start with some introductions. So besides what I just said, for the audience to get to know you better, can you tell us a little bit more about your career path? What brought you into AI?
Oh, okay. Yes, my career path. I graduated, I got my PhD in computer science from Duke University. And I think that's when I really started to get really serious about kind of natural language processing and AI. Although, I always have been interested in mathematics, physics, and the language arts. But I guess that's it's not really coincidence, because I can share you, like, when I thought about this, I thought there's a story about my childhood I probably can share with you. Was when I was little, I like to draw some symbols on the paper, okay? And I would tell my parents, okay, what these symbols mean and how I could put together them to make different meanings. But this was before I could read and write. But I grew up in China, right? So, but these symbols no way look like Chinese characters. They look more like tadpole. So we call it tadpole language. So I was in my little world of tadpole language, and really had no idea of AI, certainly back then. But then if you think about it, there's some interesting connection from back then and now what I'm doing. So today I'm actually developing computer algorithms and models trying to get meanings out of human natural language. So I thought that's just some kind of a interesting, connection. Like maybe back then I was already interested in AI.
I think so.
Wow, Joyce, that's great. That's a great story. So I actually grew up in Ann Arbor and went to the University of Michigan. And while I was at the university, I was taking courses in computer science and psychology. And I got really interested in the connection between computer science and psychology and trying to understand, in a computational sense, what does it mean for people to think? And this was earlier than when she went to Duke. And there was less formal knowledge about computational theories. This was not when AI just got its start in the 50s, but it was in the 70s, and then I went to graduate school in the 80s. And still, we are continuing trying to understand how you can think about people and how they're thinking very much in terms of one step after the other, or even in modeling them in neural networks and things like that. And so that's always been something that I've been very interested in. I went to graduate school and was able to continue my work, start the real work on how to study AI. And then coming to Michigan, I've spent my professional career here doing research in artificial intelligence.
Well, thank you. These are great career paths. And tonight is about teaching robots. But before we even talk about teaching robots, maybe we can clarify a little what we mean about robots. In general, what we see is the views that are popularized by the media and of human-like machines, if you imagine Star Wars or iRobot. But what do you, as AI researcher, mean when you say robot?
Fine, I'll go first. So when I think of robot, usually, I do think of something that has the ability to often move around through the world, although not always, but usually to manipulate the world and to sense the world. So some of the robots we've used have been ones that are just a robot arm, and then they have a vision system. Actually, the Kinect vision system from the Xbox has been a big tool in research. But I am myself not a robotics researcher. One of the cool things about being at Michigan is we have so many people with so many different levels of expertise. And I've been able to take advantage of some robotics researchers and being able to use their robots that they've developed. So when I think of a robot, it will be something that is usually manipulating the environment and sensing the world. And just as a little plug that Michigan has a robotics institute all on its own, and there's a big, beautiful building going up on North Campus, and so they're going to be moving that into that next winter, well, in 2020.
Yeah, so I'm also not a roboticist. My research is really in language processing, but I definitely echo what John just said. In my view, I think that robot would have some unique properties. The first property is the physical bodies, okay? So it may not have the body of a human, okay, but it has some bodies that you can touch, you can feel. And the second, certainly John already mentioned, is the perception, right? So be able to perceive from the environment, whether it's auditory or visual or haptic. And then the actuator, the third is the actuator, is to be able to take actions, so it could be navigation, moving, or has an arm, then can manipulate and pick up things and all that. Another thing is the sort of the mapping between the perception to the action, because it can perceive from the environment and also make decisions of what to do. So then there's the robots. Actually, before I started working with the roboticists, I thought robots are smart, okay? But then after that, I feel like, oh my gosh, So they're, in fact, these mapping function, very often they're just pre-specified. They're just programmed, okay? It has to be, using some kind of a formal language and so on. So this kind of a mapping function, we really want to, the intelligent robot is about, to be able to learn and to map better from the perception to action and make decisions and all that.
And another thing I think that we both react to is we want to have the robots making decisions on their own. And a lot of times when you see videos of robots that are amazing, like the Boston Dynamics robots that flip around or pick up things, often they are actually remote controlled by a human. So the human is actually telling it at every step of the way what to do. Now sometimes they're more autonomous, as we say, and even some of the robots we've sent to Mars, initially when they were up there, they would wait to get commands from Earth, which take a long time to get there. They would get those and then they would execute them, and then they would be sending back video to Earth, and then that would go around. One of the things that's happening is they're making robots now when they send them into space that are able to do more on their own. So that they can use their perception in order to make decisions about avoiding obstacles and things like that. So I think and I think both Joyce and I, it's funny that she said that, is when we both got into this, it's not that these people haven't done great work, but they actually have had to focus so much on the perceptual side of, it's so easy for us to look out into the world and see all these people and separate you from your chair and from the background. But for AI systems, that's extremely difficult, especially to continually do it and track things in the real world. And so that's been a very big research problem for over the last 30 years. A lot of progress has been made in the last 5 or 10 years. And similarly, on the control of the actions that they do, being able to, one of the research projects at Michigan is a walking robot. That is, the first walking robots, each time they took a step, they were always stable. So They would have a step, they'd be stable, they'd move their foot, they would shift to that other foot. But the new robots are often running or whatever so that they are not stable at every point. And so Jesse Grizzle is one of the faculty members in the Robotics Institute, and he has a robot named Mabel, I believe, that is really doing a lot of research on how to create these kind of running or walking robots. So all of that we want to be consumers of. So we're not doing the control of these low-level motor joints or doing the perceptual processing. Once we've got that, we want to ask, how can we get these robots to do useful things for us? And so surprisingly, most of the robotists have left that to us to do. So, and there's a lot of people who are interested in this as to how to do this more cognitive aspects of having robots doing multiple tasks.
Actually, picking on that, on the more cognitive robots, and going again forward with my earlier point that a lot of what we know about robots these days is coming from this media view, from movies. There is this tendency to make very strong analogies between humans and robots. So robots often look like humans, but we do know that they are quite different. So in particular, when it comes to thinking, how are robots and humans different? And how they think about environment, or how they perceive, how they do this cognitive processing.
So my research is actually trying to go in the direction of using what we know about humans in order to build smart robots. So there's a subfield of AI called cognitive architecture. It's not about designing cognition, but it's about what is the underlying building blocks of cognition. So there's computer architecture is about how to build computers. This is how to build AI systems. What are the primitive components you use in order to build up cognition? Now, a lot of work recently has been on neural nets, or something you might have heard of, deep learning. And that really is mostly neurons that feed to each other. And that's been very powerful. But what we know about the human brain is that it's not just homogeneous, lots of neurons. It's not just billions and billions of neurons. There's a real structure there. And so I'm more interested in what that structure is, how the different parts of the mind actually work together. So we're going to do a parlor trick right now. So I want you to imagine something, and we'll walk through it. And don't get upset if you can't do it, but most people can do it. So imagine the word wow. Now flip it upside down. When was the last time you saw the spouse of that person? Now, for some of you, it might have been a while ago. For others, it might have been very recent. How about you, young lady? How recent was that for you?
I can see you right now.
So the point is that you used a lot of different cognitive capabilities in order to solve that problem. It wasn't just you went from my words directly to an answer. You had to do some manipulations of data in your mind. So you started out being able to hear my voice. You were able to translate that. Usually people are able to translate that into the letters W-O-W in your visual space, visual area. And then you were able to do this operation, which you possibly never did before, or nobody ever told you to do before, is turn it upside down. But given the smiles on many people's face, I think you did it, and you came up with the letters M-O-M, and then you were able to use that to go to what we call semantic memory, which is your knowledge about facts about the world, and you were able to extract out that that was this person, mom, well, this word mom, and then you were able to go back there and possibly get some idea of who that person was, and then go back again and go back and get what the spouse of that person was. And then you were able to go, and all the time you're getting language from me, so you're processing that, so that's all going on in the background. And then you're able to go what we often call episodic memory, which is the history of your experiences in the world. And that's what you're able to access to say, okay, that was the last time I saw them, or I've seen them right now. And so you're using lots of different parts of your mind, and they're not just one soup. And so for me, trying to figure out what are these different pieces and how do they work together is a lot of my research. And one of the reasons I'm interested in what we're going to talk about later, which is how to learn from language, is just like that problem, it involves almost all aspects of cognition. So it's really forcing us to put all those pieces together. So that's my parlor trick.
Yeah. So this is probably not just for robotics, but for general AI. There are two types of AI. There's the strong AI, there's the weak AI. So the strong AI is really trying to develop algorithms that more like human thoughts or human decision making and human behaviors. So John has talked about this human aspect and a lot of models that can actually motivate the computational models. And also for the weak AI, it's not really looking at how humans do, but really trying to define a narrow problem and then define some kind of a criteria, success criteria, and develop algorithms just to try to make agents to achieve such kind of a criteria, such as we've seen chess playing like the Go, AlphaGo, and some other like machine translation and all these applications. They're more in the area of the weak AI. And the excitement we have experienced today is probably more of the success of the weak AI, and we're still kind of far from the strong AI.
Right, and I think both of us want to go
Yes.
into the area we are because we want to be able to progress from the weaker
Exactly.
AI to the strong AI.
Yes. So we need to understand, build our models based on our understanding of all these, cognitive processes of human models. Yeah.
So you mentioned the different thinking components that we have, like episodic memory or visual processing and all that. But there is also, of course, knowledge that we have and use in making all these decisions. So can you tell us a little bit more about how people organize and use this knowledge as relevant to what we can do about robots? How should they organize and use such knowledge?
Okay, I can start with
Go
something.
ahead.
Okay, so I think there has been a lot of studies on how human organize knowledge and make inference. There are different models, right? There is like logic-based inference, so they capture the knowledge in terms of some kind of a proposition for first-order logic and all that, and use the logic inference. So for example, if we know all cars are expensive and Mazda is a car, then Mazda must be expensive. So this kind of a logical inference, there's a name for that, for modus ponens, to do this kind of inference. And then there's other types of inference, cognitive science, and studies have also demonstrated very useful in human thought process or organizing knowledge. For example, Bayesian models. So Bayesian models is more of like statistical reasoning. So if you see some evidence you want to predict the hypothesis, then humans sometimes tend to go, apply the Bayes rule, trying to look at, what's the likelihood of the hypothesis generating or produce that kind of evidence, and what is the prior knowledge about this hypothesis, so put these together to make the inference. And these also some like models we use in computer modeling as well. So I would say like quite a few of these models that cognitive science studies in terms of human cognition or human knowledge and the inference that we do also use in computational modeling.
And one of the areas that has grown a lot recently is using, trying to have models of neurons and large numbers of neurons, millions or so, and being able to train them to, say, look at a picture and then give a response as to what's in the picture. And usually these involve training them on many pictures and training them for a long, long time in order to sort of capture the information that's in the picture. So that's become very popular. From my standpoint, it's great on the perception side, but it's not so great maybe on some of the other kinds of reasoning we humans do, like in episodic memory or the semantic type of structures that we get back when I ask a question of who's the spouse, when we don't really have a lot of training information on that. But I think one of the things about AI is, although every once in a while we all go in a certain direction as certain things become popular and they seem to be successful for a while, AI has many different techniques that we are exploring in order to try to build robots and AI systems. And we are still, I would say, in the Wild West days, where even though AI has been going on for over 50 years, there's still a lot we don't know, and we're still trying to figure out how to put all the pieces together to get intelligent robots. And we talk about robots because that lets us have perceptual systems, and we have to do robot control. But there's also similar types of things that just work with software. So sometimes they're called software agents or whatever. And so they are maybe things like checking to make sure that somebody who does a credit card charge, that's not being used fraudulently. So they're looking at where the charge is, how much it is, what the pattern of behavior the person has done in the past, in order to make a decision as to whether or not they should let that charge go through. So AI is easy to think about in terms of robots, but there's a lot of AI, which we're not going to talk about today, which is not in robots, that is out there helping with businesses and even in medicine and other areas. So, but I just don't want you to think that that's just because we're interested in robots, that's all of AI these days. It's a very broad field.
Welcome for more Friday Night AI.
Exactly. We
So
got lots of things. We'll keep you going. Yeah.
Yes. Okay, so now we have a understanding of your view, or your as researchers' view of robots. So we can get closer to how to go about teaching robots. And that really means that robots have ways to learn. So what are the different ways in which robots learn today? And if we could also see some examples from your own work on robots learning task.
Yes. So in my lab, we're so in my lab, we're developing techniques so we can teach robots the similar way as we teach humans. So how do we teach humans? We use language and we demonstrate, right? So we want to be able to do that with our robots. So this is just show you a couple of quick demos. This is a demo that we show to, we teach the robot how to learn some verbs, okay, the meaning of verbs, like place. So this is our Baxter robot. This is what Baxter robot sees.
I don't know how to do it. Could you show me?
Sure. This is how you do it.
After the action,
So we saw the ambiguities from the environment.
Yes.
Sure, I'll try to reproduce this action, put everything back, and say ready.
Ready.
I'm going to perform this action. Let me know if it's correct.
Yes, that is correct.
All right.
Place the tropical juice on the cutting board.
So it doesn't understand tropical juice.
It is the pink bottle.
When you say tropical juice, do you mean that bottle?
Yes.
Sure, I will perform this action. Let me know if it's correct.
So this is just through language communication and a demonstration.
Yes, that is correct.
Just wanna, let's see, another quick demo is to show like we humans have a lot of knowledge about cause effect. When we drop the glass, it's likely to break or something, but the robots don't have that. Agents don't usually have this kind of cause effect knowledge. So how do we give such kind of knowledge to the robot? Because it's very important when they try to learn and tasks. So this is a quick demo to show that.
Hi, baby. Hello, can you teach me how to make smoothie?
Yes.
What is the first step to make smoothie?
All the Java Juice people in the audience are going to get real nervous
Peel
now.
the orange.
Sorry, I am not familiar with this action. Please show me what the orange looks like after peeling. How would you describe the effect of this action?
Now the orange is peeled. The skin is removed.
Got it. Here are some images I found. Please take a look at my screen. Which of these images show a peeled orange?
The first, second, and fifth.
So give some small number of examples to learn.
Okay, I will learn from these images. What is next to make smoothie?
Next, you put the orange into the blender.
Okay, what is next to make smoothie?
Next, you turn on the blender.
Did you first close the blender lid?
Good question.
Detect the change of the environment. Okay. Well, that's just a quick demo. So, Joe.
Oh. Well, thank you. So normally when I give a talk, I start off trying to motivate this, which is that someday, not from us, but somebody will be delivering robots to you and your house, and it will do a lot of things that it comes pre-programmed with, but there's going to be things that you want it to do, like solve little puzzles or make smoothies. And so we want to be able to instruct them because you're not going to want to do the programming. And so how many people here are programmers? So part of the goal of our research is to put you out of business, I think. But I wouldn't worry about it anytime soon. But that's sort of the idea, is to make it more possible for regular people to get control of their AI systems and get them to do what they're going to do, want them to do. So what we're going to show you right now is one of the things we've looked at is how do you teach an AI system to solve different problems. Now, in the news, they talk about AI systems that can play and learn to play very well games like Go or chess. And that is fabulous work. What we're trying to do is take a tiny step at the very beginning, which is teach the robot or the AI system what the rules of the game are. So when you come up to, if you have this system that learns how to play Go, and you say, I want to play tic-tac-toe, there's nothing. It's just going to play Go with you. What we want to be able to do is create these AI systems that can do lots of different games and that you can teach them the game from scratch. And so what I'm going to show you, this is not a game, but it gives you the idea. This is a puzzle. The puzzle's called Tower of Hanoi. How many people have heard of Tower of Hanoi? Okay, a lot of you. Essentially, there's discs of different sizes, and there's 3 pegs. And you can pick up one disc at a time and move it to another peg. And the whole idea is to get all of the discs over to from one side to the other, but you can only move one at a time, and you can never put a larger disc on a smaller peg. So I've just told you how to do this, and theoretically you could think about it and maybe try to solve it. And that's what we're going to try to do here, is teach this robot how to do this. And so this is done by my student, James Kirk, no relation. But there's a Connect vision system up that you can't see that is looking down at the stacks of blocks. And our robot is great, but it's not precise enough to be able to take discs and put them on pegs. So instead, we just have stacks of blocks. So it doesn't require a lot of imagination, but it's just a little bit different than the regular problem. And then let's see if I can get this started.
The name of the game is Tower of Hanoi.
Okay, what are the actions and rules of the game?
You can move a clear block onto a clear object that is larger than the block.
I don't know the concept clear.
If a block is not below an object, then it is clear.
Okay, I now understand the concept clear. I have learned the action.
The goal is that a large block is on a right location, and a medium block is on the large block, and a small block is on the medium block.
I have learned the goal.
Done.
So now it's solving the problem and figuring out. So it's internally, it did a search of its own understanding of the problem that it just learned about, and now it's just going to go and execute that. And so there's, yeah, just hopefully it doesn't drop any blocks, but since this is a video, we're pretty confident. So one of the nice things here is the idea is this is what we call a goal-based task, where we describe the goal and the system based on how it knows what the actions are and what's legal can figure it out on its own. Okay, so it doesn't have to be told step by step. And so the kind of problems that Joyce was showing are ones where it's more a what we call a procedural task. So one way I think about it is you think about baking a cake. It would be great if you could tell somebody, here's what I want you to do, bake the cake. Use all the knowledge you know about physics and chemistry and heat and thermodynamics to figure out how to bake that cake. Nobody's going to be able to do it. What they need to do is get to see examples. We have recipes. And so there's these tasks that involve sort of recipes, being told how things to do. And sometimes we want a combination of both. So the next task I'm going to show is us just showing you a completely different kind of robot. And we're going to teach it a very simple task, which is to deliver something to another room. It already does understand a map of the world, but it doesn't know how to deliver things at all. So we'll see about this. So this is by another student named Aaron.
Deliver the package to the SOAR office.
What is the goal?
The goal is that the package is in the SOAR office.
So,
Please give me the package.
so it is got this goal. It is able to figure out a little bit of how to do it, but it doesn't know how to get to the office.
How do I get to the SOAR office?
Follow the right wall until you see a second intersection.
So he's giving it very specific commands about how to solve this problem. Okay? And so just remember that. And one way you might think is it's keeping a list of all the commands he gave it.
Okay. Please take the package.
So now it thinks it solved the problem.
Please give me the state
So-
banner.
What it did is realize it doesn't really matter what the object is, and it really doesn't matter where the location is. What you're supposed to do is take the object to the location when you do deliver. So it's doing completely different path than it did before. It didn't memorize how to solve the problem. It instead figured out what was most important to solve the problem and then did some internal problem solving we call planning in order to solve it. So that gives you some of the ideas of some of the research we're trying to do. Some of our videos are a little bit old, so of course the most recent stuff is much more exciting. But that sort of gives you the direction of what we want to do is being able to interactively, what we call it interactively, teach the robot. Because in both cases, what you saw is it wasn't the human just went down a recipe and said one thing after another. What was great, I thought, about both systems is they asked questions. So when the system didn't know what to do or didn't understand, it would ask a question to get ideas from the human. And so we think that one of the most important things is don't take this the wrong way, taking advantage of the humans, okay? Meaning trying to take the knowledge out of the humans and have the robot help with them. So anyway, that's our big demos.
Thank you.
It's not showing our demos, but there's another way of teaching robots is through these kinesthetic kind of a guidance. So, for example, you can hold the robot manipulator and arm and move to certain key points, and then the robot will learn, extrapolate those key points to learn the trajectory of accomplish certain tasks.
Right. So that's called learning by demonstration. And another technique that people work on is called learning by imitation, and I think you can figure that out, which is the system watches well, actually, you had a little bit of learning by imitation and making that. So that's an example of learning by imitation. So although each of us use different techniques, I think we all understand that all of these techniques are going to be important going forward in teaching robots.
Well, thanks for the demos. I have to admit that I've seen a couple of these before, but I'm impressed every time I see them.
They still work.
They still work. But even like knowing what it takes to build these components, like putting them all together, I'm quite impressed with what they are able to do. And picking on John's last comment on things that we would expect in the future, where do you see these teaching robots going? What would be the next step that you envision that will happen in AI in this direction of instruction for robots?
I'll let you go first, Joyce.
Okay, so I think that for limited domain, we probably will be able to see this kind of language and visual demonstration, but there has to be in some constrained environment, because computer vision and all are still a very hard problem in unconstrained environment. But in the few years down the road, hopefully, we'll be able to see like machine learning, transfer learning, multitask learning, and domain adaptation will allow us to see, the technology developed for one particular constrained domain can be extended to some other similar domains, hopefully, okay? And maybe then a few years down the road, then we start to see a little more open domain. Let's say you get a robot from the box, bring it home, and then you'll be able to communicate, do a few things in your household, like teach robots different things.
Yeah, so the good news and bad news about this area is, the bad news sort of is we depend on lots of different technologies to make these things work. But all of those technologies are advancing. So vision is getting better. So being able to expand this to environments. So one of our faculty members, his name is Chad Jenkins, looks at if there's a pile of different kinds of boxes or whatever, how do you find the one that you want out of that cacophony of different kinds of boxes? And so that's not been solved and that's still an ongoing problem, but he's making a lot of progress. So right now, you'll see all of our worlds have the vision systems have very separate things, and so it's easy to pick them out. That's going to get better. As we're seeing with these other robots that are able to run and whatever, that's going to get better. One of the things we're very constrained by right now is our language processing, meaning how does it understand the language? And you might have noticed, at least in our work, the language is kind of, it's English, but it's a very special kind of English. So it's not like any of you could we do not have a live demo here today because we would not trust our system to be understanding just the way you happen to try to give it instructions. So I think that is another area where we hope to see advances where the systems are able to understand more robustly what a human is trying to communicate. So I see, I'm not worried about running out of things to do, let's put it that way. So I think we have a lot of things to do.
Yes.
And, well, just to jump really far, a lot of people talk about AI systems becoming smarter than humans in 5 or 10 years, and that's not a concern of mine.
So one final question before we open it up to the audience, and that has to do with, if we have this world where robots can learn, are there any issues with that, or possible challenges or downsides with robots that learn things?
Well, I think there's a lot of issues. One of the things that's good about a lot of software on your phone is somebody's tested it, and people know how it's going to work. If somebody can teach it to do new things, how do we know that it's still going to do the things you want it to do? And so, and the worst case is that you have a robot that has a lot of capabilities. People can teach it to do evil things. And so how do we ensure, and I'm not sure that I know how do we ensure that when people are teaching robots, they're teaching them to do ethical, legal things? And so part of that might be that we have to have the robots themselves know a lot about what's legal and ethical, but I still think that's extremely difficult for them to always know. You probably heard about Asimov's laws of robots, and those are very difficult to apply to unusual situations. So I'm not sure how well that will go. I think one thing we'll do is that we will restrict who can instruct robots or who can instruct AI systems, so that we make sure that that's going to be an issue. So I do think there's these ethical, legal issues on the horizon, and so we have to think about those. And people are starting. One of the things that has changed over the last 10 years is 10 years ago, this was a very unusual topic to talk about in artificial intelligence, but it's really become something that's very important. And one of the previous Friday nights was exactly on this topic. It was on these topics, and so you can go to our website maybe and see videos.
Yes, there is a recording there.
So, but I think this will be something we come back to over and over again in the coming years.
Yeah, I guess also just one thing to add is how these kind of robots gonna change how we human interact with each other. Because we already see some technology, right? Like if you go to a restaurant and see a family, like they're probably not talking to each other. They're on the phone and chat and all that. So I just don't know, in the future if we have, the robots that we can talk to and we can teach them, and do we want to teach humans anymore? So I don't know the answer. Okay, I think that we would like to have robots that really are part of our society, and also be able to bring the humans together, not pushing humans apart. So that, I don't know, that'd be an issue or not. It's just top of mind, yeah.
But it's useful that we'll have this on our minds as we build the system.
Yeah.
That's right.
Yep.
Yes.
And with that, we are ready for questions from you.
So we have some people with microphones.
And we have microphones. If we could please wait for that.
So, to Professor Chai, I wanted to ask, when you talk about, learning by imitation and stuff, how do you, I guess currently because of the closed environment, the robot can perceive visible change when you're moving an object to the blender or something like that. But in a real world scenario, there may be a lot of things changing in its perception. How would you distinguish, what it actually has to learn, whereas what is background noise or something like that?
Can you please repeat the question?
The question, see if I get it correctly, okay? The question is, there's how do you know when to teach the robot, right? So there's a lot of noise in the environment. You detect the change of the environment. Is that something you need to teach, or is that just the pure noise you should ignore? Is that the question? That's a very good question. I think there's a feedback loop, okay? A lot of times is we're really looking at what robot behave, and then that would give us the signal about, whether I need to teach you or not, right? So if it's the noise that the robot can detect and ignore, can still perform the way it goes, then probably we don't really have to interject or teach anything. But if it's, something the robot behaves sort of unexpectedly, maybe that's the time that human would really have to intervene and teach robots more. And the robot can also, internally, it can keep track of these different models and the output of the models, and maybe it's unexpected from the robot's point of view, should have also the self-awareness. The robot should also proactively ask, what I don't understand, or did I do right, or that kind of thing. But I think you raised a very important question, is we need to make this internal representation more transparent to the humans. The robot cannot just make decision, and the human doesn't really know why the robot makes that decision, to explain the robot behavior. I think that there's a whole new field on explainable AI is really trying to address this kind of a problem. So make the internal representation transparent so that humans can really get humans' involvement in this process. So that's also the deep learning, nowadays, they're trying to, not just the black box, they're really trying to understand what happens inside the box. One of the benefit, I would think, is to really enable this kind of a human-robot communication. Yeah, thank you.
Other questions?
This question is for Professor Laird, but it could be both of you.
Great.
You mentioned extrapolation. What actually is the mechanism that allows these robots or the AI software to do that kind of extrapolation? And then I have a second question.
Let's do one at a time.
Okay.
So you can also repeat it, please.
Sorry.
So the question was, what allows robots to do the kind of extrapolation I was talking about when the robot was able to internally solve the Tower of Hanoi problem, and then it went out and did it in the world. So it builds a representation of the problem inside of the computer in terms of data structures. So it will have a representation that says there's a block in this location, there's empty spaces here, and there's a block on top of that block. And then think of it as it's a simulator. Is it simulating what will happen when I move this block to this position, and what happens when I block? And it will do a little search here, and it will try things out. And it will find that if it moves a block in a certain location and then another one, it gets into a stuck position. And so it says, well, that's a dead end. I'm going to back up, and I'm going to try a different path. And finally, for this problem, there's only 3 blocks, and so it turns out there's not a lot of possibilities there. It finally finds, and by doing this search internally through these representations it's built up, it's able to find that it gets into a representation that meets the description of the goal that the person gave to it. So one of the important things that gets glossed over in that video is when the person is describing the goal, it says, I'm not going to get it, it says that there's a large block on the right location, there's a medium-sized block on the large block, and there's a small block on the medium-sized block. It's actually looking at the situation, and it's realizing that that is the goal situation initially when he's doing the instruction. So that's why he picks up the blocks and moves them over to the initial. So it's able to recognize both when it achieves it in the real world, but also in this internal simulation it's created that it's achieved the goal state. All right, so think of it as the computer simulating these possibilities and trying out different alternatives inside, because it's much faster for it to do that. I mean, it could try to pick up the blocks and move them, but that's very slow. So whenever we can get the computer to do it internally, it usually can do it much faster as long as it has a pretty good model of how the world works. But sometimes the world has its own ways that the computer doesn't really understand everything about the physics of the world.
Just the other thing was, it's my understanding right now that there is kind of a dual track going on in AI.
Okay.
One is deep learning, the other one is dialogue management systems, and nobody's quite sure which one's going to lead us to the strong AI. Is that correct?
So I wouldn't say that there's those 2 tracks only. I'd say there's a lot of tracks going on. Now, one major track has been the success of what's called deep learning, which is this where we use neurons and we use models of neurons in order to try to make a mapping from perception to some classification or things like that. So that's that works very well when you have to just do some pattern matching and then produce some output. When you try to do language, that works for very specific cases, but if you want to have an interaction that's back and forth, This is actually solving a different problem. Dialogue management, which is actually part of Joyce's expertise area, is how do you decide what to say next, given what has happened before and what's happening right now. So those are two problems. I would say that there's a lot of people putting a lot of money in deep learning right now. In fact, there's billions of dollars going into it. But we don't have to solve AI in order to have success. And so I think people start to get tied up in thinking that only when we get human level intelligence have we been successful in AI. And there's a lot of technologies that have been developed over the years that will not lead to human level AI, but they're useful for solving this kind of problem or that kind of problem. And so we should more celebrate all the different ways we can build AI systems to solve different kinds of problems.
Yeah, just want to add also on that is because you talk about language dialogue, right? In order to carry conversation with you, I need to understand you to a certain degree, right? So the deep learning approach have been applied to just to learn the input and the output, to do the dialogue management. But then there is also the issue with just in general natural language understanding, the inference part, because we humans use a lot of common sense knowledge, common sense reasoning to do, to understand what we're talking about, to gauge in conversation. But machines are really not good at that. Yeah, so that today, there's still a lot of effort, research effort has been devoted in this area. Yeah.
And then another part of it is that the next step is part of the more sophisticated dialogue management system, I hope, like us, has a little bit of, we're building up a little bit of representation internally of who you are and what you know. And so we assume a certain level of education here, and we sort of use our explanations to that level. So if I was talking to a 5-year-old, the kind of explanations I would give would be very different. And so that's one of the things humans are able to do right now, is build up this mental model of the people they're interacting with, and also what did I teach you before? And a lot of the AI approaches that we're using right now haven't gotten to that level.
Other questions?
Hi. Well, this is a good segue. I really liked the part where the demo, it came back and said, are you going to put the lid on the blender? And so when you were talking about how kids learn and stuff like that, you sort of observe and make ask questions and all that kind of junk. But one of the things that kids start doing is they start asking why you're doing things. And so like when you're putting the kettle on, normally at some age the child would say, why are you putting the kettle on? And then at some point or another, maybe, they would go, oh, you're putting the kettle on, let me grab the tea. Because they've already anticipated that that you're in the process of making tea again. And so have you done, is there also work being done on making the things more anticipatory? Where they go, I know what I'm capable of, and I can assist. That kind of thing.
Can you
So there are AI, so the work we have done so far has not gotten to that area, but there are systems that really focus in on how to systems. I'm sorry, the question?
So are there
question
systems?
was, are there systems out there that try to anticipate what the human is going to need when they're interacting with them? And that does require, once, as I talked about, having an internal representation, a model of what the person knows and what actions they're going to do in the future. And definitely that's an active area of research. So human-robot interaction is one of the fields that covers part of what we do. And so people are definitely interested in those types of things. And that is, so part of this is learning, a lot of this is learning, having the computer, the robot, build up a richer and richer simulation of the world. They build a simulation of people in the world, of what they're thinking, but also of what the coffee pot can do or what the stove can do, and build up on that. And this is definitely research going on, but it's not all come together. Unless Joyce did it last week.
Yes, it's a very good question, and there's different levels of anticipation, right? So the kind of anticipation about you're talking about, like really about the cause, like effect, that kind of anticipation, still like really ongoing research. But then there's let's say, for example, there's some other type of anticipation. For example, the earlier like air travel system, right? So when you ask where you're gonna fly to, so the system actually when the system asks a human, it anticipates that human gonna say something about like places. So it actually used that kind of a knowledge, try to do the language modeling to help the speech recognition. Okay, so these kind of anticipation has been used in the system development. Yeah.
Other questions?
You're next. Yes.
I have a question for Professor Chai. So we saw the video where, for instance, you have the robot that learns how to grab the orange, put it in the blender, turn on the blender, right? So the whole command, right, is a set of different tasks that the robot is learning how to do. So does it learn like a representation, like in language, for each of those different tasks, or like for the whole command?
So the question is, does the robot learn a representation for each of the tasks or for the whole command?
Right. So it tries to learn both. Okay. So the task level is some hierarchical structure, and but then at the command level, we see like we use the verbs. Like here, it's really trying to learn is what does the peel mean? Because the peel, it really, for the robot, it means nothing, peel the orange. And it really tries to learn is what the effect this peel would cause to the orange. Okay, so that's why the human says that, okay, when you peel the orange, the skin is removed. So that is the state of the result state of this peel. So based on these kind of phrases, the machine would go to the internet, the search, okay, find some oranges, pick pictures, and then give the human ask human to pick. So this way it can build a model about what is the result of that peel, also perceptually. So it's really trying to link like the meaning of the verb to the resulting states of the world. So the reason is that this would allow, okay, this is a general representation that we represent verb this way for certain types of verbs, okay. So this way would allow the robot to do some planning. You know, once you have like a result verb, result state is a goal representation. So once you have that goal representation, then you'll be able to plan for the actions to reach to that goal. So that's the idea that we're trying to represent verbs with the result states. So we're trying to learn both at the hierarchical task level and the lower verb level.
Thank you.
I have a question about that very thing in terms of language itself, where verbs become nouns, so that in the process you're describing not the action or the process, but the only thing that the machine can deal with is the end result, and that is a noun.
Yes, exactly. So there are different types of verbs. There are manner verbs like jump, walk, okay, these kind of manner verbs. And then there are result verbs. Result verbs like pick up, chop, and all these change the state of the objects that the verb takes. So we look at is those result verbs. We're really looking at is the end result of those verbs. But I think that for certain verbs, the procedure, the manner still matters. But right now, we're just looking at the result part.
Is there a point at which humans then imitate this in their own language processing? Because that, in my understanding of linguistics,
yes,
when that happens, that's the death direction of a language.
The death direction of a language?
Yeah, where the language begins to weaken. Where verbs themselves, have a life or have, a process, and take us forward, and that it limits our own imaginations of going forward, period, with human activity, in thinking in terms of nouns and flags.
No, well, I would not say that in thinking of the verbs just as nouns. This is just one aspect we try to model, but verbs are rich,
Yes.
absolutely rich. We're not saying verbs, just this one aspect. Verbs, there's the frame semantics. We use frame semantics to capture the semantics of verbs. We try to capture all these kind of information like agent, patient, instrument associated with verbs and temporal relations and all that. But this is just one aspect we try to explicitly model. Yes, it's just one. It's not the whole story.
Okay. All right.
Okay.
And this was my original question. When you had given the example of WOW and flipping it around, and then who was the spouse when I went through that process, my father is deceased.
Sure.
And that brought a feeling.
Yep.
Or interjected a feeling into my thought process. Now, how does this work into how a machine is going to be able to understand human language or inferences? I think you brought that word up.
So I'm going to interpret your question.
Okay, thank you.
And just very broadly. So question is, how are we going to get emotion into machines?
Okay.
That's not what you said, but I'll take that. So I think one of the things we're trying to understand is how does emotion influence thought? And that is something in philosophy, psychology, and computer science. And there are multiple theories of emotion these days, and one of them is what's called appraisal theory, which is we're always examining the situation around us and seeing how that affects our goals, how it affects other people, and things like that. And that is not just a rational thing, but it does change what we think is important and how valuable something is to us. And so these things combine together, and we get a physiological response. I'm not sure we're going to have those kind of responses in computers, but it's very important, I believe, for learning, because one of the things you find in people is that when there's a high arousal situation because of emotion, they remember things a lot more. And they also seem to have sort of emotional responses to wanting to learn things. So curiosity, what is that? And so we try to come up with mathematical formulations of these things as to how to combine the sensory information coming into the computer and how that interacts with what the computer's goals are. And although we don't have what's called a hot emotion like in humans where it's physiological, we try to understand how should that influence the thinking of the AI system. So this is clearly not settled, but it's something that is an active area of research. There's a question way in the back. Is that right?
Yes.
Oh, wow.
Thank
you very much for your question.
Regulatory solutions as ways to protect AI from ethical problems, ethical challenges. You mentioned that only certain people might be able to teach them, right? Which sounds great, but here we are 70 years into software development. There's no sign of any equivalent to what they have in civil and mechanical engineering of certification and the ways which engineers can be proven to be ethical or responsible for their work. And I don't think we're going to see that type of leadership from industry. So my question is the academy, is research ready to either put the brakes on or lead the way in establishing regulatory bureaucracy to ensure that there's some sort of framework by which the people who are given tools that literally have ruined the world, we're all living through it, right? That how can the ethics, the problems that you're addressing, be built into a regulatory framework that would actually try to help with the absence of ethics on the part of industry?
I think that's Rada's question. So the question is.
Fix it.
So I think these are real problems, but I don't think that, and I don't think there's easy solutions to this. I think that there are, right now, as you notice, that there's not a lot of economic incentives for industry to ensure ethical behavior by, well, humans and by software systems. So I think this is an area where we have to, the academy and industry and government have to come together to try to think about solutions. And I don't think that, I think it's a mistake to say, well, the academy or researchers solve it. I don't think that's going to work, and but I also agree that it's not going to work by putting it off on other people. So it's a joint responsibility. And I'm a little optimistic because this is an issue. There have been organizations created. There is an AI organization of major companies that are trying to come up with at least some kind of codes of conduct in terms of building AI systems. Whether that's going to have any teeth or not, and I don't know, but it's definitely, it's important for people like you, or for all of us. It's not people like you. No, it's important for all of us to recognize this problem and try to engage it. Is that a punt or what?
Other questions?
So my question is about data collection. I'm wondering how you're going to get the large quantities of data that you need to train AI. Do you imagine people are walking around with Google Glass and they're kind of transmitting all this data to some kind of centralized network or server, or you just have a lot of graduate students in a room telling it instructions, or people solving CAPTCHAs? Like, how do you get all this data that you need to this artificial intelligence?
Well, we have to tease apart the problem, right? Because we're building a system, and this system actually has quite a few research problems that we're looking at. For certain problems, we can get data. For certain problems, we probably cannot get data, okay? So for example, when we interact with, let's say, this Baxter robot, like try to collect language instructions, and we can use some simulated Baxter robot and put it on the crowdsourcing and collect human language instruction just based on the language instruction using these kind of simulated Baxter robot, and then we'll be able to build models. So for that part it can be done. Okay, that's also some data set is already available there. But for certain part, like directly interact with the robots, it will be very hard, to collect large amount of data. So what we usually do is to invite human subjects come to the lab and really, have to go through some IRB approval, and subjects have to sign a consent form, and then we can collect some data on how they interact with our robots. So it really depends on different focus, different problems that we can have a different strategies. So that's also some of deep learning approaches cannot, not be able to apply for some of the problems because there is not large amount of data available, okay? And we really also have to understand the fundamentals of these problems. And sometimes even formulate the problem by itself is not easy, because there's so many connections with all these different problems, okay? Just carve out a little piece of a problem that is self-contained and the students can work on it, okay? That sometimes take a lot of time too. So this is a really exciting field, just so many problems, and a lot of times we just have to really define the problems, to really understand the problem and define it, and then look at what would be the best way to address it. Yeah.
And I think that's a very good ending note. It is a very exciting field with a lot of problems to address and think about, and if you still have more questions, you can still linger around for just a little bit. Before we end, I would like to say that if you have suggestions for future topics that we could address in future Friday Night AIs, we have some cards outside, and you can leave a note with your suggestion. I would like to thank the Ann Arbor District Library for their partnership. And of course, thank you to our wonderful speakers for sharing their experiences.
Thank you for coming. It's great to be here. Yeah.
This has been a great experience. I want to thank you for your questions. It's great to have an attentive audience. And really, to reiterate what Rada says, we actually have a lot more faculty in AI at Michigan, and I think the two that have come before were ones that, what experience they had were what drew Joyce and I to come here, is that it was a great experience, and I will definitely tell them that other faculty should do this. So hopefully you'll come back in future months, and we'll be able to cover other topics throughout the year. So being engaged with the city, I think, is just a great thing. So thanks.
Absolutely. Thank you. Thank you, Rada, too, for organizing this.